All right, let's take a look at our lesson for today. We're going to look at sequences and summation notation. And summation notation has to do with series, sequences and series. So let's do some vocab first. This first page is pretty much mostly vocab. A sequence, this is just a definition, if you will, of a sequence. It's an ordered list of numbers. And each number of the sequence is known as a term. So that's a vocab word. If we talk about a term of the sequence, it's talking about one particular item in the sequence. A finite sequence, so the word finite will probably, kind of cue you in on what's happening there. It's a sequence that ends. It has a specific number of terms. It doesn't keep going and going. Maybe it has 5 terms, maybe it has 50 terms. I mean, I don't know. It has a specific number of terms. An infinite sequence, on the other hand, is a sequence that never stops. It just keeps going and going. It has an infinite number of terms. It is possible for an infinite sequence to approach a particular number, and that concept is really is referring to a limit. It's a limit. And if it does, the sequence is said to converge. These are vocabulary words. So converge means that the sequence is approaching a particular number. If it doesn't converge, then it's said to diverge. Again, these are all vocab words. So if we talk about a sequence converging, it means that the numbers as they're listed approach a particular number. If it doesn't, then it diverges. So it doesn't approach a particular number. The nth term is basically the formula. It's like the equation that generates the terms. It's called the nth term. Nth term is a word that means that's the formula that's going to produce the sequence. Now these two right here, these are two ways to write the formulas. Okay, let's talk about these two ways. These are pretty significant. Our default, so in other words, if the problem doesn't mention what kind of formula to use, then our default is explicit. That's the kind of formula that we write. This is important for you to write down because I have had students before that believed that they could write a recursive formula. A recursive is a very specialized formula and it has to be asked for. So let's just write this out. So this one is our default. So if it doesn't say what kind of formula, then we know it means explicit formula. Recursive is a specialized formula, and it must be asked for by name. It has to say, write a recursive formula. Okay, it has to be asked for. So let's look at the difference between the two. We will look at the difference between the two with some examples, but for the explicit formula gives the nth term, that formula, the nth term, as an a sub n. It's a function of n. It just has n in it. So what does that mean? That means that if I wanted to know the 50th term, I could just put a 50 in for n and I would find the 50th term, would be fine. A recursive formula is a very specialized formula. It gives one or more of the first few terms. It lists them. So it gives one or more of the first few terms, and then it defines the terms that follow using the previous terms. This is a very specialized kind of formula. We would only write it if we were asked to. Okay, so two different kinds of formulas. Any questions on that so far? Okay. Partial sum, another vocabulary word, partial sum. A partial sum is the sum of the first blank terms, and you can just S of 5 is the sum of the first 5 terms. S sub 7 is the sum of the first 7 terms. That's what that means. Partial sum. It's just adding up a few of the terms of the sequence. It's called a partial sum. And the number that's listed right here refers to the number of terms that are added. Okay. A sequence of partial sums, which we're really not going to look at this year as a sequence of partial sums, is if we found, like let's just say we found the first, I don't know, 7 partial sums, and we listed those numbers out, and we found a formula for them. That's what that's talking about, the sequence of partial sums. We're really not going to work with that this year. So the sequence of partial sums is basically just a concept that we're looking at. We really aren't going to have problems on sequences of partial sums. So let's look now at some special notation. This is the Greek letter sigma. This is sigma notation, and it means sum. This right here means sum. Basically it's our command to add all the stuff up. We're adding from our, whatever this happens to be, our first term, which doesn't have to be the actual first term, it could be the 5th term, and then we add to the nth term, whatever term that happens to be. Okay, so the lower and the upper, that's what they're talking about. So it kind of makes sense. The lower one, the one on the bottom, is the first one of the terms that you would add up, and the one on the top is the last one. And then you would just know that you'd have to do all the ones in between. Okay, all the ones in between. So that's called sigma notation or summation notation. Now, these properties, this is just kind of good to know. We really aren't going to be working very much with adding these sigma notations together. It's just for your information, just kind of FYI. So we could split that up into 2 being added. We could split this one up into doing them separately and subtracting them, and C, which is a constant. So hopefully we're good with that vocabulary word. Constant means like a number, like 5 or whatever, 2, a constant. We are allowed to pull that outside the summation and then apply it afterward. So just again, another concept to be, just aware of. As far as factorial notation goes, let's just briefly talk about some factorial notation. I know we've talked about factorials before, or you've heard of factorials. If we were going to do, say, I don't know, 4 factorial would be, just as a reminder of how it works, would be 4 times 3 times 2 times 1. That's how factorials work. They start with the number that's stated, like the 4, and then they decrease by 1 every time they go down, and you multiply them all together. 1 factorial makes sense to be 1. The weird one here is 0 factorial. I don't think we're going to be dealing very much with 0 factorial, but just so that you know, 0 factorial is actually 1. And this is showing how you would break down, expand. This is being expanded. How you would expand in factorial. It's not a number, is it? It's a variable. So the way this is expanded, this is how you would expand 1 that's a number. Okay, 4 factorial, 4 times 3 times 2 times 1. In factorial would be n times n minus 1 times n minus 2 times n minus 3, like forever, right? Until you get all the way down to 1. And these are just concepts to be familiar with that you might be applying in our work. Okay, are we okay? All right, let's take a look at some examples then. So on number 1, it's asking for the nth term, which means find the nth term, which means that we want to generate a formula. we want to generate a formula that will create that sequence. Now, it's not saying what kind of formula, so what is our default? Explicit. This is an explicit formula. This is not a recursive formula. Okay, it's explicit. So I'm just going to kind of take you through the thought process here. Perhaps you recall from, I don't know, from previous that there's like arithmetic sequences and geometric sequences, and then there's something called neither. Okay, we're dealing with neither here, which I think are far more difficult than the ones geometric and arithmetic, because you've got to figure out the pattern. It's not like adding something every time or multiplying something every time. You actually have to figure it out. So I think they're a little bit more difficult. So we're starting with the neither formulas. Yay. Okay. So when we look at fractions, my recommendation would be, and let's just kind of write this down. So when we have fractions, okay, my recommendation would be, number one, to look at, just because it's a shorter word to say, I'm going to say top and bottom. I'm talking about numerator and denominator, right? Those are just longer words. So I'm just going to abbreviate, look at the top and bottom separately. Okay, separately. Don't try to take it in as one thing. Look at them separately and see if you can figure out a formula for them separately. And always, when we're doing this, when we're generating formulas, number two, I would recommend to write the term number under each term. Okay, these are recommendations that I'm giving you. I'm writing them out for you, okay? And this works, number two works all the time. Number one is just for fractions. Okay, so I'm going to start by writing the term number down underneath. This is term number one, term number two, term number three, term number four. Why would I do that? Why would I write term numbers down there? Well, because the formula that I have to come up with in my brain will have an n in it. And so the n, whenever I put a 1 in the n, it's a 1. I put a 2, it's a 2. 3, it's a 3. 4, it's a 4. So I've got to figure out what in the world to make, how can I make n look so that when I put a 1 in it, I get a 2. When I put a 2 in it, I get a 4. When I put a 3 in it, I get a 6. When I put a 4 in it, I get a 8. So we're looking for a pattern. What pattern would work there? If I put a 1 in it, I get a 2. If I put a 2 in it, I get a 4. If I put a 3 in it, I get a 6. A 4 in it, I get 8. What pattern would that be? Times 2, right? It would be n times 2. So we're going to start by looking at the denominator, because that one was a bit easier to work with. So I've got my fraction, and I know the denominator is 2n, because when I put the term number in, it generates the proper numbers in the bottom. Now, which is the denominator. Now the numerator is another thing altogether. But what I would like to do is I would like to compare, in this particular case, that's why these are hard, because I can't tell you the same thing to do every time. They're all different. So when I look at the top number, I'm going to compare it to the bottom number and see if there's a pattern. So if I compare 1 to 2 and 3 to 4 and 5 to 6 and 7 to 8, do we see any kind of pattern there? Aren't they all 1 apart? Right? Isn't the numerator always 1 less than the denominator? So then what I would do with my formula is I would say 2n minus 1. Now this one, as formulas go, was pretty hard to do. I'm just telling you, this one is kind of hard. The ones that are neither are kind of hard because you really have to think through and determine how you're going to come up with that. Okay, we'll do one more. So I'm going to start by putting the term numbers underneath here. So the term numbers, so I can kind of start thinking. So a 1, a 2, a 3, and a 4, and a 5. Okay. The signs do something called alternating. Alternating. So let's add something to our list up here. Number 3. If signs alternate, write that part separate. Okay, if the signs alternate, write that part second. All right, so let's see what, I'm going to start writing that part. So I've got a sub n equals. The alternating part is -1 to the n or -1 to the n plus 1. I mean, those are our choices. Or you could do -1 to the n minus 1. But typically we do -1 to the n or -1 to the n plus 1. If I write it to the n, let's see if this works. If I do -1 to the first power, do I get a negative number? I do, don't I? -1 to the first power is negative. What about -1 to the second power? Do I get a positive number? Okay, -1 to the third power, I get a negative number. So this is called the alternating part. This part is the alternating part. And it's either going to be -1 to the n or -1 to the n plus 1 for us. Okay, that makes it alternate. Either negative, positive, or positive, negative, depending on which way it's going. Now we can forget about the signs and just think about the numbers. Think about the numbers 2, 4, 8, 16, 32. Let's think about that. Okay, so there's several ways to get 2 from sticking a 1 in something. Couldn't I do 2 times n? We're just going to play. So if I did, let's say I did 2 times n, let's see if that works. So 2 times 1 is 2, that works. 2 times 2 is 4, that one works. Is 2 times 3 8? No. Okay, that doesn't work. That's a good try. It was a good try, but that one doesn't work. Let's see how else we can do. How else could we get those numbers instead of multiplying by 2? Think about some like 3, turning 3 into 8, and turning 4 into 16, and turning 5 into 32. We got any ideas? This one's not that easy either. We just have to think through that. What would happen, let's just play with something else. What would happen if I did 2 to the n? Let's see if that would work. So 2 to the 1, that's 2. That checks out. 2 squared is 4. Okay, that looks good. How about 2 cubed? What's 2 cubed? It's 8. And 2 to the 4th is 16. So there we go. That's our missing piece. So it's actually 2 to the n. Now, I am allowed to write it like this. It's okay. If I want it simplified, or I can write, since these both have the same exponent of n, I can write it as -2 to the n. Either one of those is perfectly fine, whichever one you prefer. Okay, how are we doing? I guess we're probably starting with the hardest part of it first. Yay, everything else is not going to be this bad. Okay, it's not bad. It's just delightful, right? We're gonna figure out how to write formulas, which they're calling nth term, for neither functions. All right, so let's look at the next one. We're supposed to list the first 4 terms of the sequence. Okay, we can do that. So a sub 1 is the first term. See, what am I doing? I'm putting a 1 right here, and I'm going to put a 1 right here, and I'm going to put a 1 right there. That's what I'm doing. That's my first term. My first term, I put 1s everywhere the n is. So I've got a to the first equals -1 to the 1 plus 1 times 2 over 1. Okay, we need to clean that up. We need to simplify it. Let's see, -1 squared is a positive number, and so that just gives me 2. So my first term is 2. I'm going to pause here for a second, make sure we're all okay. Okay. My second term, I have -1 to the 2 plus 1 over 2 over 2. Okay, so let's clean that up. Let's see, -1 cubed is a negative number, so that's -1. Okay. My third term, I have -1 to the 3 plus 1 over 2 over 3. Let's see, -1 to the 4th is positive, so I have a positive 2/3. And my last term, my very last term, let's put 4's in there. So I have -1 to the 4 plus 1 times 2 over 4. That simplifies to be, let's see, -1 to the 5th is -1, and 2/4 reduces to 1/2. So I have -1/2. So I want to ask a question before we move on. Is this an explicit or a recursive formula? Explicit or recursive? Okay, this is explicit because it doesn't list terms for us, and it doesn't make us find the next term by knowing the previous term. Recursive, like I said, is a very specialized kind of formula where the only way to get the next term is knowing the term before it. So in this case, this one is explicit. This is an explicit formula, which is our norm. That's our default, is explicit. Okay, so now let's investigate recursive. Let's talk about recursive. Here we go. Here's a recursive formula. So let's kind of see and look to see, how do we know that this is recursive? What are the clues? What are the clues? How do we know how it's recursive? Well, number one, we have a list of terms, which could be a list of list of terms. Okay, recursive formulas have to have at least one term listed, at least one. And number two, we have, we need the previous term or terms to get the next term. Okay, this right here, that signifies, that means, we need to understand what this means. This means previous term. That's what that means. If I'm looking for the fifth term, I need to have the fourth term, the n-1 term. Okay, that's how I know that it's recursive. Okay, so that's how we know it's recursive. So now let's use this recursive formula and come up with the first three terms. Well, they gave us the first term already. I mean, they had no choice but to give us the first term. So now we're going to find the second term. A sub 2 equals 3 times a sub n-1 is a sub 2 minus 1, which is, and maybe just for this first one, maybe I'll go ahead and just plug this in. A sub 2 minus 1 plus 2. Okay, which is 3 times a sub, let's see, 2 minus 1 is 1, and a sub 1 is this, is that. A sub 2 minus 1 is a sub 1, and a sub 1 happens to be 1 in this case. So we've got 1 plus 2 is 3, 3 times 3 is 9. Our third term. So we've got 3 times a sub 3 minus 1 plus 2 is 3 times 3 minus 1 is 2. A sub 2 is 9. And that's 11 times 3, or 33. So this one happens to be that number right there, because it's a sub 2. Okay, so I want to pause here for a second. Recursive, like I said, very specialized, and you would only write one like this if you were asked for it specifically. Okay, questions about recursive? Okay, so on number 4, I'm going to show you how to do this with and without the calculator. I'm going to show you how to do it without the calculator first. Okay, you need to be able to do it both ways, with and without the calculator. So what is this saying? This is saying, let's just write it in words. What is this saying? This is saying add up all terms starting at term number 3 and ending at term number 5. That's what it's saying. Saying add up all the terms starting at term number 3 and going all the way to term number 5. Okay, so let's write those out. We're going to do it by hand first. So the third term would be where I'd put a 3 in for j, so 1 over 3 plus. The fourth term would be where I'd put a 4 in for j, so 1 over 4 plus. The fifth term would be where I put a 5 in for j, which would be 1 over 5. And, okay, so I'm not going to make you find a common denominator and add all those together, like by hand, but I know that would be fun. You probably want me to, right? No, never mind. That's actually 47 over 60. That's how much those all add up to be. We're doing it by hand first. Okay, let's do part B by hand, and then we'll go get the calculator and do them on the calculator. So again, what does this mean? It means add at start the first term and add all of them up all the way to the sixth term. I need to put a 1 in where there's a k. Okay, I'm looking at this. Are we seeing any k's? There's no k. Okay, so what does that mean? That means that the first term is 2, and the second term is 2, and the third term is 2, and the fourth term is 2, and the fifth term is 2, and the sixth term is 2. I mean, that's what that means. They're all the same. I know that's weird, but that's what that means. Okay, so let's see, what if we add all that up? So 2, 4, 6, 8, 10, that would be 12. And that's the sum of the first 6 or terms 1 through 6. All right, so let's get, we good? Okay, let's get our calculator. And I want to show you how to do it on your calculator. If it's a non-calculator problem, you can certainly use your calculator to check your work. So we're going to add the calculator. The easiest place that I have found to get the summation notation is in this little button right here. The palette o math right here. And see where we have the sigma right here? That's the summation notation, the sigma. And then you simply just fill in the blanks. Now I'm going to use an X, not a J. Please use one of the gray letters. Don't use these white letters. So the variable X, on the first one we're going from 3 And our formula, I like to do fractions. So our formula is 1 over x. Again, I'm using x instead of j. And I want to go all the way to 5. And then we let the calculator do its thing. And we get the answer of 47/60. Okay, let's try the other one. Let's see if it behaves. I don't know if it's going to behave at all, but we'll try. Go to our palette. Here's this. We're going to do x goes from 1, and we just have a 2 there. Goes from 1 to 6. Let's see how smart the calculator is. And it was able to do it. It's 12. Okay? So I just wanted to make sure that's one thing. We'll do more on the calculator in this unit, but that's one using sigma notation. Okay. So last problem. Now we want to write this sum using sigma notation. So we know we have a sigma. Okay. I just kind of make it look like an E thing. I'm not really good enough to make it look so pretty. I bet you also look much better. That, I'm not really good at that. I mean, that's how it's supposed to look. But I usually just, do this. So we go from something, so we'll do N. I like N better than K. You can use whatever letter you want. I'm going to do N. See how they used a J and a K? I don't know. I like N's. I use N's all the time. N needs to start at something and go to something. And look how they're all roots. There needs to be some kind of a root. Okay. Well, if I make it root N, then what would N need to start at if I made it root N? Would it have to start at a 3? Because that's the first one. It started at a 3, and it would go all the way to what? How far is it going to go? Yep, to 77. And that's how we would translate. This is expanded from expanded form into sigma notation. And it says sigma notation. Or summation notation is another way to say it.